Hello everyone and welcome to today's lecture, and we want to talk about bases today. In the last lecture we saw how we can determine the dimension of a vector space with the help of the number of linearly independent vectors, and today we want to see something called a basis. So the idea for the basis is that if you have n linearly independent vectors, that is my vector space V has n linearly independent vectors, then any element of that vector space can be written as a linear combination of those linearly independent vectors. So what do we mean by it? Let's try to see in another manner. That is, our vector space is V, right? And a set of n linearly independent vectors in an n-dimensional space and is called a basis. So the reason we are calling them basis, as we wrote earlier, that any element on that vector space can be written in terms of those basis vectors. So let's try to see it. Let's say I have a element called, let's say, A, and this is the element that belongs to the vector space V, and my linearly independent vectors for V, that is my vector space V, these are, let's say, denoted by 1, 2, 3 and so on. And note that we'll be talking about finite dimensional case only here. That is, the vector space has finite dimension, and maybe in the later lectures we will try to generalize these ideas to infinite dimensions, but let's now just focus on finite dimensions. So the idea is that we can write A in the following manner: I equals to 1 to n. Let's say this is an n-dimensional space, and we write AI and I. This is a summation. This is a linear combination. So this idea is actually similar to the idea you are familiar with in ordinary calculus or ordinary vector courses. And the way to see it would be, think of, so let's just write it first. Think of 3D Euclidean space. Euclidean space. Oops. So if we do that, we can draw our axes, that is our x, y and z axis. So let's take this one to be our x axis. Okay, this is not a perfect drawing, so let's take this color. So let's say this is our x axis, this is suppose our y axis, and this is our z axis. And let's now try to draw a vector from here to, let's say, right here. So this is some vector, and let's denote it with b, for example. And this b vector can be written as the linear combinations of these unit vectors I, j hat and k hat, right? And this is a three-dimensional Euclidean space, and at the same time we have three linearly independent, because these guys are orthogonal to each other, that is at a 90-degree angle. So we have a three-dimensional vector space as well, and this b vector can be written in terms of this I, j and k's linear combination with different coefficients depending on the components of the b. So we have okay, let me get rid of this. So we have written our vector A. Again, let me reiterate that our vector A was written as I, and these are the vectors we are calling the basis vectors, right? And in that sense, this can be called components. Now we want to show that this expansion is unique. So the way to prove is that, let's say I could write A as the following way. So 1 to n. Instead of A, I will now choose different components, but the same basis vectors, because those are my linearly independent vectors. And let's say I could write it like this, and by comparing these two equations, I could write I equals to 1 to n ai I is equals to I equals to 1 n ai prime I. And from here you can easily see that these two would be equal, but let's try to do it in a more formal way. So the more formal way is the following. And this is just the null vector, right? But this I, this is not a I is not the null vector. So this means these guys are equal to the components of the null vector, that is 0. And remember that 0 times 0 is also a 0 vector, because if you think of this 0 ket as a column of zeros, then multiplying anything will just give you back a 0. So that's why it's a 0. So this expansion is unique. That's what we proved. So let me cut this out. Similarly, what we can do right now is that, let's say I have two vectors. Let's say a1. Okay, let's not write a again. So let's take some vector b. We write it as I. And if I don't put n over there, doesn't mean it's an infinite dimensional. space. So some of the writers never use this n, but let's try to stick with it because we are dealing with an n-dimensional vector space. So let's write it as this, and let's say we have another vector called c. They are written in the same basis, ci I, and if I want to add them, I just simply write down this whole thing, and this will be something like this. So what happens is that when you write two vectors in the same basis, you can add them component wise. And similarly for scalar multiplication, let's say this a is a scalar, so a is a scalar, scalar multiplication. So a is a scalar and a times b is just sum over I equals to 1 to n a times bi I, just like this. So this is how we can scalar multiply using these expansions, and this expansion will give us several advantages when we deal with more vector and something called linear operators. And this will be it for today, and I will see you guys on the next lecture. Thank you.